this video, we talk about the concept of system. It is not an exaggeration to say that the concept of system is the most fundamental concept in thermodynamics. And every other concept is defined for or about a system. So it is critical to understand the concept of system and define your system properly when you solve a problem. When you have trouble solving a problem, then you always examine whether your system has been defined properly, whether your definition of the system has caused any difficulty in mathematics, any inconvenience, or your definition of system is flatly incorrect. System and control volume. We have several things to talk about this concept. Now, a system can be a quantity of matter or a region in space chosen for our study. Now, these are two different definitions. One is you follow a matter, a quantity of matter. You follow a bunch of atoms that are kept in your consideration. That's when you can define a system as a quantity of matter. When you define the system as a region in space, you're only concerned with the space, the spatial boundaries of your system, and then you allow atoms to go in and out of the spatial region that you define as your system. Okay, so a system does have boundary. Either you define as a quantity of matter, or you define as a region in space. So the boundary can be real or imaginary surface, and the surface defines the system, and the boundary separates the system from the surroundings or the rest of the world. So the surroundings to a system is everything outside that system. It's the rest of the world besides the system. Okay, then we can have a closed system, which is a system that has no mass crossing the boundary. So naturally, when you define a specific set of molecules or quantity of matter as your system, you're defining a closed system. Now, even though that closed system may have its boundaries morphing, its boundary may change, may move in space, but no matter, no atoms would cross the boundary of a closed system. In contrast, we may have an open system. An open system is such a system that you allow matter to cross the boundary of the system. That makes it more complex in most cases than a closed system. Now, we may also introduce another concept. It's called an isolated system. An isolated system is a closed system that also has no energy exchange with its surroundings. So you may imagine a sealed container, and the container is also insulated, well insulated. The container is well insulated. There's no heat transfer. There's also no work crossing the boundary. And then the system inside that boundary is a isolated system. Control volume is just another name for a open system, a system that has only definition of its region in space. So it's a closed system, a control volume is a defined region in space, or in other words, it's an open system. Now here, let's see an example. This is a very common example in classic thermodynamics analysis, a piston cylinder enclosure. Now, the piston cylinder enclosure includes a cylinder, which is this part. I'm going to see if I can draw with my pen. Okay, so this is the cylinder, the contour of the cylinder. And this blue thing is the piston. And even though the piston can move relative to the cylinder, there's perfect seal between the cylinder and the piston, so that no matter will leak through the gap, or there's no gap between the piston and the cylinder. And the matter is typically the system that you're considering. So it's a misnomer to call to refer to such a thing as a piston cylinder system, because that's kind of misleading. It's dangerously misleading, because in this case our concern is probably, in most cases, is what is the matter inside the piston cylinder enclosure. We do not typically concern ourselves with the piston, the blue stuff, and the cylinder, the bold yellow, the bold black lines. So all what we're concerned with is the mass, the red matter that's defined within the dashed line rectangle. And this system's boundary can move because the piston can move in and out of the cylinder, but there's no mass leakage. That's a closed system. Here's another example. This is an open system. Here the open system is defined as a region in space. The space is inside a pipe. Now part of the boundary of this region is defined as the cylindrical surface, as you can see from the dashed line here. Okay, so this is the cylindrical part of the system's, the open system's boundary, and this part of the boundary is physical, because there's a inner wall, there's an inner surface of the pipe. However, this open system is closed. This open system, this control volume, also has two imaginary surfaces in its boundary. That's the entrance. This is the entrance. Okay, I cannot write properly. Okay, this is the entrance of the of the open system, and then this is the outlet or the exit of the open system. So that's a example of a open system or a control volume. We're interested in the region bounded by the dashed lines, and we allow matter to go in and and come out of the control volume. So always remember, we can illustrate. We should. It's always helpful to be able to illustrate a system when we try to solve a problem, and we typically use dashed lines to represent the system's boundary, and we need to remember that everything inside the dashed line, the boundary, is the system, and everything outside is the environment or the surroundings. Now, here we have an example. I'd like to invite you to take a look and take some consideration and practice. Here we have a gas trapped in the piston cylinder enclosure. There's no leakage, and the question is, should we see the gas inside this enclosure, the red thing, as the system, or should we consider the piston and the cylinder as part of our system as well? Now this depends. It depends on what we know about these things, and what we want to find out about these things. If we are concerned with any properties of the piston or the cylinder, that it may be necessary to include the piston and cylinder into our system definition. However, in the introductory thermodynamics course in engineering, the safest consideration is to think a pure substance system, which we will talk about in a separate video. The introductory engineering thermodynamics is only concerned with a pure substance system. So that immediately excludes the piston and the cylinder from being part of the system, because that would make the system not pure. The gas is something that can be pure, but if you include gas, piston and the cylinder in a system, you no longer have a pure substance system. Okay, but the more general principle is that whether you include something in your system or not depends on your objectives and depends on the information you have.